Hello. It is the 4th of March, 2016, and this is episode 45 of the Unseen Podcast. Tonight, we will get into a number of discussions. Well, we'll get into at least one discussion, maybe many, about fast radio bursts. This has been International Fast Radio Burst Week. That's what I've officially declared it. But before we do that, let me just say a couple things. First of all, we did not have an episode last week, and I apologize for that. That was just bad luck not having a panel. Coming up in May, not very far away, we have our Douglas Adams special. If you are interested in being on the panel for that, please let me know. Email unseenpodcast@gmail.com or come on over to the community on Google Plus and let us know you'd like to be part of that. We have not sent out the call for panelists for that yet. That will come out in April, but by all means, if you want to be on that, and I don't mind having a larger panel for that, by all means, let us know and we will get you on that. It should be, as usual, any discussion of Douglas Adams is very jolly. So, tonight, joining me are Adam Synergy Smith.
Hey, Paul. Hi, everybody.
And James Garrison.
Hi, Paul.
Now, I'd like to point out that James has signed up, at least tentatively, to do our April 1st podcast. So, think of some jokes for James. Or at least some questions for James. I don't know what that one's going to be about, but that's not my problem. Marsha Barnhart.
Hello, Paul. Hello, everyone.
And Nick Nielsen.
Hello, Paul, and hello to all the Unseen podcasters. And
James is already thinking about what he's going to do on April Fool's Day. I think we're probably going to have Neil deGrasse Tyson on that show. That's the plan right now. I like to get my full jokes in early. Hey,
yeah, now watch me be able to pull that off.
You know what? You should try to pull that off just to make an ass out of me. I'll
email him tomorrow.
Which is not particularly difficult, by the way. My kids do it every day. Okay. Now, tonight, as I mentioned, we wanted to talk about the really interesting developments that have been going on lately in the radio astronomy world. And it may or may not have SETI implications. Right now, I'm leaning sort of against that idea, but let's talk about that. There's been a lot of activity lately in the professional literature about fast radio bursts. Now, let me give you a little background on fast radio bursts. In 2007, an astronomer named Lorimer and his team reported on a fast radio burst. Now, they actually mined this out of radio telescope data from the Parkes Radio Observatory in Australia. And unfortunately, we don't have any Australian panelists tonight, but if David Grigg were here, he could brag about it a little bit. But the Parkes Radio Observatory in Australia has actually discovered the majority of these bursts, but not all of them. But the Lorimer burst, as it's now called, was actually occurred in 2001, and it was by far still the largest, most powerful burst that anybody's found. But since then, there have been, Adam, tell me if I got this wrong, about 17 bursts discovered, mostly by going back to the old data that had been recorded at these telescopes in what they call the High Time Resolution Universe Survey, which is this survey which tries to find very rapid radio events. And they found, initially they found just this one, which was by Lorimer and his team. And then that sparked a lot of interest in other astronomers, and the young astronomer, Emily Petroff, who's from Canada, I believe, but she's now working in Australia. she and her team have been going through the park's data and actually trying to catch them in the act. And in 2014, they caught the first one in the act. They didn't find any counterparts in any part of the electromagnetic spectrum to that burst. And then, but there have been a number reported since then in the literature. And last year, a person who's not a radio astronomer named Michael Hipke and his team found that these bursts all seem to have a certain property in common, that something called the dispersion measure, which is a measure of essentially it's when you look at the arrival time of this burst in the radio telescope and how the frequency varies with arrival time. It's something called dispersion. That's something that the physicists fully expect to happen. That at different frequencies, the arrival time should be different, especially if it's coming from very far away. And Hipke's team found that the bursts that were reported to date, that was last year, all kind of lined up in these clusters around a multiple of a certain dispersion measure. And I won't give you the math details, but now then later on, a few months after Hipke, a number of other bursts were reported, that some of which lined up with his clusters and some which didn't. And then the most recent interesting thing was, well, actually, there's a couple of recent interesting things that just happened the last couple of weeks. Adam, do you want to talk about the host galaxy discovery and the controversy about that?
Yeah, sure. So last year, again using the Parkes radio telescope, they discovered a fast radio burst while they were looking for pulsars. They regularly searched the night sky using the Parkes radio telescope for looking for pulsars, and they found a fast radio burst. This one is called Fast Radio Burst 150418, which means it was discovered working backwards on the 18th of the 4th, 2015. The thing about this particular fast radio burst is that 2 hours later, the Australia Telescope compact array, which is in New South Wales, saw a fading radio glow in the same region of the sky. And so using the two different telescope arrays, they were able to triangulate a source, which they've never been able to do before. They also used the Subaru telescope in Hawaii to track down the source galaxy, and they pinpointed the source as being an elliptical galaxy some 6 billion light years away, so very, very distant, away across the universe. And the astronomers used this dispersion measurement that you were talking about. Radio signals from celestial sources propagate across space to us here on Earth before they reach the telescope. And these radio waves, or indeed any electromagnetic signal, although space is a vacuum, it's not completely empty. There are cold ionized, there's a cold plasma of ions, electrons, essentially, and this slows down the signal as it reaches us, and it does it in such a way that it delays the signals as a function of its radio frequency, so that instead of all the frequencies all arriving at once, the higher frequencies arrive first and the lower frequencies arrive later. So you get a kind of a whistle going from a high frequency to a low frequency, or a chirp. And the astronomers can use this to measure the amount of matter in between us and wherever the signals come from. And so they were able to measure the amount of matter, first of all, in extragalactic space, to see whether it matches up with our theory of how much matter there is in the universe. And it did quite precisely match what we would expect, something around 4.9% of matter in the universe is ordinary, what we call baryonic matter, the ordinary stuff that we're made out of. So they were quite chuffed with that, because it confirms the it's called the lambda CDM model, the cosmological model of the universe. Lambda means dark energy, CDM stands for cold dark matter. And so there was a lot of cheering and flag waving about that. But unfortunately, there's been problems, basically, with this discovery. It centers on the pinpointing of the source, the elliptical galaxy. Other astronomers have looked at this galaxy, and originally it was thought to be a very quiet, passive galaxy with no active radio sources. And that's why they were able to pinpoint the fast radio burst as coming from there and nowhere else. But it now looks like this galaxy has what's called an active galactic nucleus, which means it's radio loud. So it could be that, in particular, the afterglow that was detected from by the Australia telescope probably came from the active galactic nucleus and not the source of the fast radio burst. So it looks as though they haven't actually managed to pinpoint the source of this particular fast radio burst, which is a disappointment, but it doesn't mean that someone in the future won't manage to achieve this feat. I think it's only a matter of time. Probably within this year, I would expect them to nail it. It's just one of those things. Science is hard. We know that.
Right.
What part of the spectrum, what part of the electromagnetic spectrum do the fast radio bursts appear in?
Radio.
Well, the radio.
Yeah, near in the radio astronomy band, which is near the 1.5 gigahertz, but they actually found the counterpart more like 5.5 gigahertz. So yeah,
So is this the kind of thing that the kind of radio emissions you get from active galactic nuclei, or is it believed to be some kind of other natural process that generates this kind of radio signal?
Well, it looks a lot like an active galactic nucleus, although not a super loud one. But they vary all over the map. So it's still. I mean, I don't think there's anybody's got a slam dunk here. This is something the radio astronomers are going to probably be arguing about for quite some while. And the next step, as Adam points out, is to catch another one in the act and keep doing that until we have a definite host galaxy identification. In fact, this one is controversial, but I don't think it's a done deal that they're wrong. It's just that.
Well, wasn't there some talk that it was repeated, and that's
that's a different one, but we'll get to that in just a moment.
Oh, okay.
Yeah, that was a different fast radio burst, which was discovered not at Parkes, but at Arecibo in Puerto Rico. Yeah.
Okay.
The problem is these bursts are they're very brief. They're a few milliseconds, so you need a sensitive radio telescope to find them. because the amount of energy we're talking about is tiny. Although the burst itself is actually a decent amount of energy, it only lasts for a very brief time. And
it's something like the total amount of energy that our sun emits over about 10,000 years.
Well, depending on how far away you think it is, right? I mean, yeah.
The one that they pinned down to this elliptical galaxy, it's estimated to be 1.3 times 10 to the 42 ergs, which, as I say, is around the same energy as the sun emits over 10,000 years. But that was just in 1 millisecond. So it's very, very powerful.
Yeah, it is
extremely powerful.
There's a lot of reason to believe that there's a highly energetic event, even if it's not that galaxy.
There's a Scientific American article by Lee Billings that was just, it looks like it's published the 2nd of March, so just a couple days ago, that quotes James Cordes of Arecibo, that this could be due to a neutron star in a tight orbit around a black hole.
Could be. I don't think that's a done deal either. I think that...
certainly it's not a done deal, but the interesting thing about that is this comes at a time when we have just in the recent past been able to demonstrate the detectability of gravity waves. So there is an alternate. If it was a neutron star going at a black hole, that would be the kind of thing that would generate significant gravitational forces and potentially could be seen by gravitational wave astronomy.
Right. Well, there's two things about that. One is that particular burst was before LIGO was really turned on. So they wouldn't have any data, but there is some hope that in the future there will be a fast radio burst that will, and yeah, something we have to get some perspective on is that the number of telescopes in the whole planet that can see fast radio bursts reliably is a small number. And the amount of sky they can cover is tiny. So that one estimate by Emily Petrov's team was that there are several thousand going off every day. But because we are only looking at a tiny part of the sky, we're seeing only, maybe one or two a year. Maybe a few more than that now that we're looking for them actively. But the dream is to find one that also corresponds to an event on LIGO, which is now, up and running and active. So, and by the way, my sources tell me that LIGO has seen other events other than the ones that they've reported on, the one they reported on recently, in last month. And that was, but they're still doing the analysis and they're still doing the peer review to make sure that those are real. They want to be very careful not to report anything publicly that might be a chimera. So, they don't want to be fooled by randomness, so to speak. So they are looking very, very closely at those, and it turns out there may be a lot of them, and they may have to set up a processing pipeline, kind of like Kepler, that will carefully screen out the false positives. And so there could be lots of those events out there. Could be coming in once a month or so. So there is a hope that at some point we'll see a fast radio burst that corresponds within seconds to a gravity wave. And that would nail it down as a kind of important catastrophic event. But the problem that we have with that is the most recent result, which is reported by, I think the corresponding author is Jason Hessels. And this was reported this week and it was called a repeating fast radio burst. So, Adam, are you familiar with that?
Yeah. A graduate student, Paul Schultz, was sifting through some archival data from Arecibo, and he was looking at data from last year, from May, June 2015, and he ran it through a supercomputer. He's at McGill University in Canada, and he was running an algorithm that searches for pulsars, fast radio bursts, that sort of transient radio signal, and he found several fast radio bursts in a repeating signal, 10 in fact. This has never been found before. All the fast radio bursts that have been seen in the past have been one-off solitary events, although they've, like at Parkes, they found one fast radio burst, carried on observing for days, and never seen another one. But he found 10 repeating fast radio bursts, which is a complete one-off. It's unprecedented. So this looks like it might be some sort of new subclass of fast radio burst. It looks like it might have a different astrophysical origin. It's possible that some fast radio bursts are neutron stars, or neutron stars collapsing into black holes, colliding with black holes. But the fact that this particular fast radio burst repeats means that it was also very bright, a lot brighter, and with a different spectrum to all the other fast radio bursts. So maybe this is not some cataclysmic event. It's got to be some sort of high energy astrophysical, if it is astrophysical, which I think it probably is. Maybe it's something like a flaring magnetar, or some sort of orbital event around a black hole or a neutron star. It's too early really to speculate, although I'm sure there'll be plenty of astrophysicists writing papers right now.
We're going to speculate about it right now. Actually, I'm looking at the paper. There were 11 bursts that they detected. The most powerful one is the most recent one. Most of these were detected on the same day, which I believe was June 5th of last year. I'm going by memory there. Yeah. You have to understand about Arecibo. Arecibo is this big bowl in Puerto Rico, and they can't really steer the telescope very much. They can only steer it a little bit. So it sort of sweeps by a source, and then it's gone. It's kind of like a grander version of the Ohio State Big Ear that used to be that was so important in the 60s and 70s. And they discovered 11 of these bursts pretty much all in the same direction. Now, the interesting thing about this burst is that it did repeat. It repeated 10 times. At different widths and different spectral indices, but all about the same dispersion measure, which means they're all coming from roughly about the same distance. And it sort of centers around about 560 if you're interested in the numbers here, dispersion measure in parsecs per cubic centimeter. Now, and as I mentioned, most 4 through 11 are all on the same day. So, and also within, about an hour of each other, because the Arecibo Observatory can only steer just a little bit. And the interesting thing was they had not only that was repeating, roughly in the same direction, roughly the same dispersion measure, but there's no obvious thing in the even though they're looking in the galactic plane, because that's where they were looking for pulsars. That was the purpose of their survey. They didn't find anything in the galactic plane that could have been causing this, so they think it's probably extragalactic.
Well, if it's already been established, it's about 5 billion light years away. It's got to be serious.
No, well, that's not established. You look at the dispersion measure, but you can't be sure because you haven't identified a source.
No, but the dispersion measure strongly suggests that it's extragalactic.
It does
prove that it is.
Yeah,
it's very strong. It's strongly suggestive that it's coming from way across the universe.
Well, Adam was talking earlier about the measurement of its passage through the matter between presumably a very distant source and ourselves. I assume you mean passage through the intergalactic medium. Wouldn't passage through the intergalactic medium be rather different from passage through the interstellar medium within the Milky Way?
Yes, and they can identify.
Yeah,
they know pretty well how much dispersion you get going through the galaxy, because the local galaxy, because we that we can measure pretty effectively.
Well, from what I was reading, they said that they thought it came from the direction of the constellation Auriga, so they know how far away that is.
Well, no, they don't. It could be behind that. See. So
now, Paul, you were saying about that these fast radio bursts, the ones that they got at Arecibo, had a slightly different signature, right? Like
they do vary somewhat in terms of their physical characteristics, which suggest that there's something kind of chaotic and strange going on. But it could be what they suggest is a very young source that that's still kind of coalescing and forming. So
if it was a rotating neutron star, it wouldn't necessarily throw out the exact same signature each time. It might kind of riff on it.
They don't think it's not a pulsar like a rotating neutron star. It's not that.
It's a chirp.
It's a chirp, but it doesn't have what they look for, a period. They look for some kind of regular repeating rhythm, and they couldn't find it. So it's something more chaotic than that.
Not just something spinning around, in other words.
Yeah. I mean, pulsars are pretty easy to identify because they go beep, 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 right? You get this burst of radio, then you get silence, and you get this burst of radio, then you get silence.
Hence, an early pulsar was called LGM1 for Little Green Men 1 because it was originally thought it could have been an artificial signal.
Well, it had that kind of regular rhythm that you would think you would come from an artificial signal.
Yeah, it was only 1.33 seconds between the bursts.
Right. These are spread apart in a way that doesn't make any sense in terms of periodicity, although that with more study and more observation, perhaps that would be you could find some kind of underlying pattern, but they only have 11 of them right now. So I think one of the purposes of this paper was say, here's the case for making more observations of this source.
So the question is, given the fact that you were just saying that Arecibo just swipes by and only catches these things, what other instrument would be the appropriate instrument to get a better fix on them? And maybe get
Green Bank or Jodrell Bank or 1 square kilometer array is in place. Although it's pretty high up. Well, it's about it's 33 degrees in the northern hemisphere. I think square kilometer array can see that.
Yeah.
Has anybody looked for
square
fast
kilometer
radio
array on?
Has anyone looked for
square
fast
kilometer
radio
array?
Sorry. Go ahead, Adam.
I was just going to say that the square kilometer array should be able to see fast radio bursts pretty much every day once it's up and running.
Yeah.
Until then, it's going to take Arecibo and Green Bank probably together to triangulate the source, and then it's going to take follow-up, looking for optical, gamma ray, X-rays to pin down.
Right.
What exactly
you want to catch this thing in the act, right? Not just find it through data mining. Catch it in the act, and then you can swing everything over onto it and try to find a counterpart.
Yeah, they should coordinate. They should coordinate.
Well, they do. They do.
At one point, to just gloam onto that particular part of the sky and hang out and listen for whatever time that they can spare. A concerted effort, you would think.
Well, they do that. In fact, for this recent gravity wave discovery, there is some evidence that there may be a gamma ray counterpart, which is surprising but interesting. And so people are looking at it. The reason it's surprising is these were not very high mass black holes, so they shouldn't have had a huge amount of matter sitting around the outside of them, so it shouldn't have had a big gamma ray signature. But apparently there was a gamma ray burst that occurred just about the same time. So that's still under study. Nobody really knows what that means, or it could just be coincidence. Coincidence is something that happens all the time in real life, so you have to be careful.
Well, what other than a star could be giving out that much energy that would be detectable? What other than a star would do that? That's my question. Everybody's talking about
which energy is that? I mean, you talking about the fast radio burst?
Yeah.
Well, a star doesn't put out that much, depending if it's as far as we think it is.
A neutron star.
It could be neutron stars doing something exotic.
But it would have to be something that big.
Yeah.
Why? I don't know why.
But it has to be small. We know that because something that's only a few milliseconds in size has to be a compact source. It can't be a large, because the speed of light is,
how compact of a source?
Well, the speed of light is 300 kilometers per millisecond, right? So if you're talking about something on the order of milliseconds, and you're talking about something on the order of hundreds or maybe thousands of kilometers in size, it can't be or smaller. It can't be that big. So it's smaller than a big star. It's smaller than any star, really. It's got to be something on the order of a neutron star or a black hole causing that kind of something in the vicinity of a neutron star or black hole. It could be something like a white dwarf getting sucked into a black hole. There's a lot of models that are being studied right now. Those are all really difficult to calculate, and so kind of have to stay tuned on that.
If this is coming from an extremely far distance, like 5 billion light years, wouldn't there be the possibility of gravitational lensing by galaxies along the pathway between the source and ourselves, which would make possible several different arrival events depending on the curvature of the signal around the gravitational centers?
Yes, it is possible, but we're not seeing that.
We're not seeing it. Well, shouldn't we seeing it? Was I'm saying.
No, I don't think you necessarily would be expected. I mean, ultimately, if you get a chance alignment, you will see these. You will see multiple images of the same thing due to gravitational lensing.
Now, sometimes it gets really, really complicated, and you get several images from several different perspectives of one after another.
Yeah, if you get a massive object that happens to line up between you and the source.
Right. Would the absence of that then mean that we've basically got a clear line of sight 5 billion light years away to the source of the fast radio burst?
Well, I'm not even sure it's that far, but yeah.
Okay, still significantly extragalactic. Well, how far
Z
is
equals
that?
0.1. I think Z was 1, something like close to 1.
Is that still in the Virgo supercluster or farther out than that?
I think it's not. No, I'm not sure.
Okay, well, another question. Didn't you first early say in this program that these were discovered in Australia and the southern hemisphere?
Initially, the first FRBs were discovered in Australia.
So we've got them. So we've got at least two sources if one's coming in the southern hemisphere.
I think there's been at least one at Green Bank. There have been a number at Arecibo.
Yeah.
Arecibo is now actually racking up quite a number because of this repeating one. Arecibo may actually be in the lead right now. Now, what we don't know,
we're talking about at least two sources then, and are they both supposed to be about the same distance away?
Oh, no. There are many. These are all different directions. So there are. We know of the one source that may be repeating. It looks like it's repeating, but all the other sources are scattered all over the sky. So the southern sky, for the most part, but they are scattered. There's only one source that's known to be the same source. And I'm sure that's really known. It's just that it's consistent with being the same source. We should say that.
Right.
It's interesting. It's interesting that there was a lot of skepticism amongst the radio astronomy community to begin with when these fast radio bursts were first detected, and that's more or less because they all were detected at Parkes. The Parkes radio telescope had problems. Around about 2010, they had something like 16 detections of pulses of radio waves, which were similarly mysterious, but in the end, they were tracked down to the door on their microwave oven opening.
Yeah, and I should point out that those had a very different signature. Those were called those peritons.
Yes.
And the people were opening the door when the microwave oven was still running, so the microwaves were leaking out, and but those were seen in multiple directions, and not necessarily adjacent directions. So it was pretty obvious those were some kind of terrestrial interference. Just nobody knew what they were. The FRBs have the proper. Yeah. Go ahead, Adam.
They're definitely coming from the sky and not coming from the Earth. But I think that the whole topic, fast radio bursts, because it was initially based at Parkes, a lot of radio astronomers elsewhere in the world were reluctant to get involved. And I don't think that's the case now, because it's become big news. I think the whole radio astronomy community around the world will get behind looking into fast radio bursts, and we'll have an answer pretty soon as to what they are.
Well, Paul, you're pretty plugged into SETI. What direction are they taking on this? What have they been doing?
Yeah, I talked to Andrew Simeon, who's one of the lead people at Berkeley SETI, and he thinks it's pretty likely to be an astrophysical phenomenon and not a SETI target. But if you give him an FRB, a definite FRB direction to look in, I think he'll probably try to get some telescope time to look at it. Mm-hmm. But it may. The general consensus is that nobody can figure out why this would be a SETI beacon, although it sure as hell looks like it could be but the problem is the dispersion measures are so large that they look like they're coming from a long way away. And the original paper by Lorimer called it an extragalactic signal, or not a signal, signal's the wrong word, an extragalactic burst. This was in 2007, now 9 years ago. And since then, the whole community has been focused on it as a natural phenomenon. Nobody knows exactly what natural phenomenon it might be. Now, I'm sure you're familiar with the fallacy, the argument from ignorance. Just because you don't know what it is, you don't get to call it what you'd like it to be. right? So we don't know what it is, but it doesn't mean it's aliens. Although,
so why is the science community so very interested in it? Let's talk about what it means. What do these fast radio bursts mean to us?
Well, that's the problem, is we don't know what it is, what's causing them. So that's why it's interesting, right?
In the same way that KIC 8462852 is interesting, because nobody really knows how that signal is generated,
right?
How that light curve is generated.
Yeah, and so when you get anomalies in any kind of data, you immediately trigger a lot of scientific interest.
This has been going on for a long time. It's just now they think that they've detected one of these.
Well,
it's probably been thrown out since eons.
Well,
but now we're just detecting it. Is that the thing?
Well, the first one that was reported in 2007, and it occurred in 2001. So yeah, they are recently. The problem is you have to have a radio telescope that's not only sensitive but is looking at these very short time slices to find data. What they were doing was they were looking for pulsars, which are a known phenomena that has very short pulses. They were doing a survey for these short pulses, and that's when they discovered it.
So are they going to have a group of scientists go back and data mine and see if farther back they found that and just didn't know what they were looking for and missed it?
Well, I don't know how far back the data goes that they can actually mine, but yeah, so they have been mining the data. Yes.
You'd have to have, particular kind of sensitive data in order to do that kind of data mining, and that level of sensitivity and refinement doesn't exist beyond a certain threshold in the past.
Yeah, but these days we have every university has the ability to do that kind of data mining on any data set they can get their hands on. So it's going to have, if there's data out there that haven't been mined, it's going to get mined before very long.
But as implied earlier, what people really want to do is find a live one and track it.
Well, that has happened. It's happened at least twice to my knowledge. In 2014, it happened, and there was a team ready to go, and they looked for it in every part of the electromagnetic spectrum that we have access to, and nothing was found. In 2015, they swung their Australian array onto that rough direction and did find this signal in a different frequency band, which I think might have been an afterglow, a radio afterglow of the original burst. That was the hypothesis they put forward in their paper. Since then, just in the last 2 or 3 weeks, there have been a lot of criticism of that paper, and there have been people who have done observations with the Very Large Array in New Mexico who have found that source is varying and is now has increased to where it's louder than what they saw in 2015. And so that may not, in fact, be an afterglow at all. It may be something else entirely. But those observations are right hot off the pressers. There's not much analysis yet. So I would stay tuned on that. I think we don't really know if the host galaxy identification that was published is correct or not.
Okay. I've got a couple of quick questions, Paul.
Sure.
All right. Is there you said that they're extremely brief durations in the millisecond range. Is there any similarity between all the fast radio bursts, or are they all different frequencies, different directions?
Well, the frequencies are they sweep through a range, mm-hmm. and the thing is that arrival time varies for the frequency. So and these receivers are very sensitive and can cover a wide range. So they'll see the burst coming in at a particular time, and then they'll see it later at a different frequency. And
but they're related to each other. They're
basically
are the same burst, just one of them's a higher energy, higher frequency.
Well, I wouldn't say high energy, but the frequency changes over time, and sometimes it starts at a lower frequency and goes up, a higher frequency comes down. But this one that's repeating does seem to have a pretty consistent pattern to it.
Well, the other that kind of leads into the other question is, do you know what they've got in place to make sure this isn't just some sort of back data noise, just something building on top of information they've already collected and just kind of causing a minor feedback or something like that?
Well, that's not an unreasonable question, and I think that if they'd only ever discovered them at the Parkes Radio Observatory, the question would be, why just Parkes? Why not elsewhere? But they have found them at Arecibo as well, where there's completely different software and hardware and everything. So I don't know. I think that there's been a lot of work gone into trying to figure out if it could be some kind of glitch in the system, and it doesn't appear to be at this point. For one thing, if there was a glitch in the system, you would see it. You would see it in random collections of directions. The thing is, the Parkes Radio Observatory looks in different directions simultaneously, which is a clever thing to do, because what that does is that lets them rule out terrestrial interference if they're worried about a satellite, somebody driving by with a loud radio or something that's interfering with their receiver. They should be able to see that and filter it out. So what they do is they, and this goes back to the days of the big ear in the 50s and 60s, which had two horns, and if they saw the signal on both horns at the same time, they knew it was somebody messing around and not, some kind of terrestrial interference, and not a celestial object. And so so this is a fairly standard practice. And what they see with the FRBs is they see them in one horn, typically. The Lorimer burst, which is a very powerful burst that they saw in 2001, reported in 2007, that burst was in multiple horns, but they were all adjacent to each other. So they were all looking in roughly the same direction. So it was a powerful burst, but it got into more than one horn. So there are ways to check that it's not just some kind of mistake. And I think pretty much all those checks have been done. Could it still be a mistake? Well, if it is, it's a mistake. Nobody's observed the same burst at two different radio sites at the same time yet, because it's so hard. You'd have to have two big sensitive radio telescopes pointing in the same direction at the same time. That does happen sometimes, but you'd have to be lucky enough to get a burst pointed, in that time. And no, that hasn't happened. They do something called very long baseline interferometry, where they will have multiple radio telescopes pointed at the same source, the same galaxy or whatever. But is there going to be a burst coming from that galaxy during that observing run? Probably not. It's a very tough problem to solve, but I think that there's a tremendous amount of work that's gone into it. I think there's a lot of confidence now that we are seeing something real here.
Is there enough interest that we can expect to see some large-scale effort like that across several different radio telescopes?
I don't know.
In the future, not right now, but I mean, sometime.
But the problem with Arecibo is the most sensitive, right? And it's pointed wherever it's pointed at a given time. Right. Parkes is a good telescope. When the square kilometer array comes online in a few years, I think we're going to have a lot more options. Now it's going to be primarily in the southern hemisphere, which is the same place as Parkes, same direction as Parkes. You could potentially cover the same part of the sky and get actually interferometry on an FRB. But we know it's a very compact source, so we're probably not going to see any kind of interferometric data on it. You can't get a 1 millisecond pulse out of a whole galaxy. You can only get out of a very small area.
Yes, that would seem to me to throw into question the idea it could be an active galactic nuclei.
Well, active galactic nuclei are probably primarily driven by black holes, which are small enough to
the singularity is dimensionless, but the supermassive black hole would have an enormous event horizon and an enormous, these sometimes power, the synchrotron radiation bursts that come out of the jets that come out of these galaxies with active black holes.
Yeah, we don't really understand, exactly where the energy how it might be concentrated. It could be in an area small enough to make that kind of pulse.
You're suggesting that it needs to be an area that small to make that kind of pulse. So I'm
suggesting a 1 millisecond pulse is not going to come out of a light year wide.
Right, and some the supermassive
something like
supermassive. Go ahead.
Go ahead, Adam.
Something like a tidal disruption event, a star falling into a supermassive black hole, would be quite a small thing. It would only be 100 to 1,000 kilometers wide, and yet you'd have a lot of energy. It'd give off a very high signal.
Yeah,
it would come from a very small area.
That's correct. Yeah, I think that it could be something like that, or a popular model is two neutron stars that have been orbiting each other for billions of years suddenly coalescing. That's a rare event, but over the universe, it probably happens pretty frequently.
Now, I have a question. There's several things that I've read about the fast radio bursts, and in almost every article I've read, they throw in this little thing, and it could be consistent with signs of an extraterrestrial intelligence. What about this would lead somebody there?
Well, it's mainly that we just don't know, right? I mean, if an extraterrestrial intelligence wanted to advertise its presence, one way to do that would be to send out a burst of very high energy over a very short time. But we would expect it would be closer to us than what we're seeing with this dispersion measures that people are coming up with.
They were sent out 1 billion years ago, right?
Well, we don't know.
But if this is 1 billion light years away, it was sent out 1 billion years ago.
Well, if it was 1 billion light years away, but the thing is, nobody has yet definitively shown to everyone's satisfaction where any of these bursts are coming from.
But they are quite certain that it's a very, very, very far distance.
Well, there's evidence for that. I wouldn't say quite certain.
Let me suggest another approach to it as a SETI problem, which is that when we, as Paul says, there's evidence that suggests these comes from a very far distance. And I like to point out that when we get these radio signals over very long distance of maybe millions or billions of light years, this is an existence proof that radio SETI is possible over cosmological distances. So I would suggest to you, if there were, I'm not saying there is, if there were a genuine super civilization in our universe that was capable of enormous astroengineering projects, of being able to move stars and planets around, one of the ways in which they could generate a signal that could be visible to the entire observable universe would be to engineer just such an event. If engineering a neutron star spiraling into a black hole and sending out a fast radio burst, they would have the technology and the science to know that this could be heard all over the observable universe.
But my God, that would be awfully ruinous to the neighborhood to engineer such a thing.
Well, if you're that big of a civilization, you can afford to expend a few neighborhoods. After all, you have to break a few eggs if you want to make an omelet.
Well, it could be done in a dwarf galaxy a long way from anybody who has any influence, right?
Anybody who can do anything about it.
Yeah.
Well, I'm glad they're 6 billion years away then, or whatever.
Well, we don't know. We really don't know how far away they are. I mean, that the
Well, they ain't in the neighborhood.
Let me trace for you the how this came about. They detected a fast radio burst, right? Then they found a fading radio signal near there that they said, wow, that could be quite near where the burst came from, close enough that it's within the error bars and could be from that burst. And in fact, there's a high probability it was from the same direction. And then they got an optical telescope on it and they said, oh my gosh, there's a galaxy there, right where that came from. So that's the host galaxy for that burst. Now, where the mainstream media got it wrong was they reported that the source had been tracked down. That was wrong. What the scientists reported was that here's evidence that here's an argument that this was the this galaxy was the host galaxy for this radio burst. And now a little more science, and we know how far away that galaxy was by using all the standard methods that we use to determine the distance to galaxies, which has to do with spectroscopy, which is looking at the light coming from the galaxy and figuring out how redshifted it is. And then so essentially they measured the redshift. And we believe there's a lot of good evidence that the redshift of a galaxy is very strongly correlated with its distance and certainly above a certain level. And this redshift was very nearly equal to 1, which means a lot of redshift. Every wavelength is stretched out by a factor of 2, essentially. So if your wavelength is 500 nanometers, it becomes 1,000 nanometers, which is a lot of stretch, a lot of redshift. So it goes from being green light to being invisible infrared light. And that is, that is the way they determined that this galaxy was at the distance it was. But, and then that was all seemed quite neatly consistent with other models, and so it seemed like a good match. It was a completely valid scientific paper. They essentially put out a hypothesis that the FRB is from this host galaxy. They did not establish what caused the FRB. The mainstream media got this completely wrong. They said,
that's a shocker.
They said we have the source and we had to have the mystery solved, right? Mystery solved. I wish they wouldn't use the word mystery at all, because we don't know if it's a mystery or a puzzle, right? A puzzle is something that we just have to move the pieces around and we sort of figure out what's causing it, right? A mystery is something where we just don't have a concept that will fit the information we have. Now, that was a very reasonable paper that came out. Here's a host galaxy we think corresponds to FRB. About a week later, other people came out saying, maybe not. There's arguments against that. And they also came up with observations that seem to argue against it as well. Those observations are very young and need more analysis. It's entirely possible. But then the repeating FRB came out. And so now the question is, maybe it's a repeating FRB that has an afterglow associated with it that comes and goes at various times. We just don't know. And so Nick is right that it could be a very advanced civilization doing things at a stellar level to send out sort of a, we were here, we were awesome, suck it. And,
I can't wait till they get our reruns of the Andy Griffith Show and stuff. Then it will show them what a stellar civilization once existed.
Oh, they're gonna show up and on the White House lawn and demand Carol Burnett. Bring us Carol Burnett.
That's right, and Harvey Korman too. Damn it. But reruns.
And this will be billions of years from now, and it won't be a White House lawn, but or a lawn anywhere. But it's entirely one of the things that the Benfords raised in their paper on Benford beacons was that it might be like a monument. It might be a way of saying we were here, we kicked butt. Kilroy was here, or Kardashev 3 was here. We got to this level. We don't know how much longer we're going to stay there, but we got to this level. We were able to smash one neutron star into another here, but if that's true, then it's a very common occurrence because we're seeing these FRBs all over the place. There's probably thousands of them every day. When I say thousands, I don't mean we detect thousands every day. There's no way our radio telescopes could do that. We detect a few a year at best. But we have, if you pretend that we had radio telescopes covering the whole sky at the same sensitivity, you would see thousands. Which has been always my argument with the WOW signal. There may be lots of WOW signals out there. We just we're covering such a tiny portion of the sky with sufficient sensitivity that we don't see them. Or we even discard them as a matter of course, because we think they can't possibly be real and move on. I deal with a lot of people who do data analysis. If they see a signal that doesn't fit their model, they throw it out.
They don't just throw it into a little "I'll be back to you later" pile?
No, because I want to point out this is an entirely rational thing for them to do, is to throw out that signal, because they're looking for particular phenomena. They have a particular job to do, and they don't want to do. They assume it's a satellite or whatever interfering with their signal, and they just throw it out. They don't even look at it. If you look at the NORAD radar that scans the skies every day, they have algorithms that throw out all the spurious stuff that's getting thrown into their antennas. Those algorithms see all kinds of interference, and they just discard it. Could one of those be the WOW signal? It could be, but they're not interested in that. Their job is to track satellites that are flying over the Earth and possibly ballistic missiles. And
so what you're looking for is going to obviously affect what you find.
Mm-hmm.
Well, it's good. It has to, because there's too much data.
You can't look at everything.
You can't look at everything. No. And that's just reality of modern day sensors. There's too much data.
We could easily formulate that into what we could call the SETI paradox, is you don't know what to look for, so you can't find it. And if you can't find it, you don't know what you're looking for.
Well, that's true. I mean, you can't form a hypothesis for something that you don't know what it is.
Donald Rumsfeld's unknown unknowns.
Yeah, well, not sure I want to credit him with anything particularly deep, but there are a lot of unknown unknowns. Yes. And I deal with this all the time in my job. I'm a space systems engineer. We spend enormous amounts of effort dealing with the known unknowns, with the probability distributions we think we understand for phenomena that we think we understand, and that's never what goes wrong. What goes wrong is something we didn't think of, right?
Well, I'm wondering if the astrophysical community is going to find fast radio bursts interesting enough to now drop some things and maybe look at that more. That might just be something that in a year they're going to go, well, that was interesting, but let's look over here for something else. I don't know how much the astrophysical community is enticed by this particular little phenomenon.
Well,
do you think much?
It's not that they have tons of money. Yeah, go ahead, Adam. Sorry. Go ahead, Adam. Have we lost Adam?
The thing is, these fast radio bursts can be used as a cosmic distance ladder in the same way that they now use supernova to estimate the distance across space to far off galaxies. If they can pinpoint the source, nail it down to a galaxy, they can use the dispersion measure to get a very good, precise distance measure. And so instead of a standard candle, we'd have like a standard radio siren to tell us how much the universe is expanding.
Mm-hmm.
It gives us information about dark energy.
Mm-hmm.
We can use the dispersion measure to precisely measure the amount of matter.
Mm-hmm.
That gives us information about dark matter.
I
and
see.
ordinary
So
matter. There's a lot we can learn.
It can become a real calibrator then.
Yeah.
I see. Okay, I understand. Yeah, that's of value for sure.
It could.
Okay.
Yeah.
All right. Yeah. Well, then I think they ought to get on it.
Well, I mean that could happen, right? But I mean, so far it's very controversial. So it's early days yet.
Well, if they see a value in it, like was just pointed out, if they see a value in it, maybe they will. But you're right. This is a story that's just beginning to unfold, isn't it, Paul? They're just starting to get their teeth around this.
Right. Well, the first paper came out 9 years ago, not quite 9 years ago, and the real flurry of papers that have come out just the last few weeks have been promising us a big advance, but maybe not. And so far, we just don't understand it very well. And it looks, by the way, I would point out that a lot of these bursts do seem to cluster at a dispersion measures that are multiples of one dispersion measure. Not all of them, but many of them do. And that's unexplained as well. It sort of indicates that, well, either a physical process we don't understand, or there's some kind of that structure to them that just doesn't make any sense right now. However, a few of them don't match up to that sort of quantization. So it's still
we need a larger data set.
We do. And that's the thing is but now that people are sensitized to this, people are going to be looking. It's just like when they first discovered pulsars. Nobody was really looking for pulsars. They just happened to stumble on them, and they said, "Oh, that's interesting. What is that?" And it took a while to figure it out. And then it took even longer to realize, hey, we should be surveying for these things. We should be looking for them all over the place. And the particular survey that Arecibo was conducting was looking for them in the galactic plane, which is why they found this one in the galactic plane. Now, it's interesting this one is in the galactic plane, which means our galaxy is kind of a flat disk. And this particular repeating fast radio burst is found in that plane. However, the people who wrote the paper make a very strong argument that it's not really coming from our galaxy. So I think the burden of proof is on anyone who wants to prove that it is coming from our galaxy. But it does fit this clustering around multiples of a certain dispersion measure that was proposed last year. So, we may have multiple classes of these things. We may have some that are just normal astrophysical phenomena, and something that are completely different.
Be interesting to come back to this topic in around 5 years, say.
Yeah.
See what's developed.
Yeah. I think this whole controversy that we've seen in the last couple of weeks has been really interesting to watch. And watching the mainstream media trying to walk back from, oh, we know what FRBs are, to where, oh, we don't know what they are. Oh dear. Oh my goodness. Oh, there's one repeating. We don't know what that is.
It must be extraterrestrial intelligence.
Well, it's extraterrestrial, that's for sure. But
extraterrestrial intelligence.
Well, it could. I can't rule that out yet. But now this is something, by the way, not related to FRBs, but to Tabby Star, that David Grinspoon wrote last week. That was published. What was it? Slate, I think it was. I'll provide a link to it in the show notes, where he makes some pretty reasonable arguments about you shouldn't treat possible extraterrestrial intelligence explanations as silly or wildly improbable, but you also shouldn't treat them first. You should look first for the natural. Just look for what you know first, and then look for what you don't know. But we do know that we do know that technological civilizations exist. We don't know that very advanced technological civilizations exist, but civilizations that can send out radio signals, we do know they exist because we have one. So it's not a violation of Occam's razor to state that, hey, this could be an ETI sending this out, but only after you've ruled out all the known stuff.
But I think the media does that on purpose, almost to increase readership. It almost seems to me that anytime they get the opportunity in science to throw out, oh, this could be an indicator of extraterrestrial intelligence, they toss that out there almost,
It's clickbait, yes.
Yeah, exactly so. And then, like you were saying, Paul, then they start walking back things. Well, it wasn't really repeating, and it's not really this, and it's not really that. And
well, some people walk it back, some people walk it forward. All you got to do is listen to late night radio, and you can find all kinds of people who are even more certain than when it was first announced. Or if the story goes away, then it's being suppressed.
Yeah. Oh well, yeah. I mean, Mike Bowler's not here, but yeah. Conspiracy theories make everything fit your model, but I think that it's way too early. My personal view is way too early to call FRBs an interesting SETI phenomenon. And I think the SETI scientists agree with that.
I'm still shocked, because I'm your village idiot here, but I'm still shocked that the Tabby Star automatically, boom, oh, this could be a Dyson swarm. How did we get there?
Well, I mean, that actually, I've written up a bit on that on my blog, the Dream of the Open Channel. It's still under construction, but it's called Tabby Star for the Perplexed. And I got some nice comments from Jason Wright just this week. Jason Wright's the guy who kind of originally came forward with the notion that this could be an interesting SETI target because it could be some kind of megastructure. However, everybody agrees, including Jason, that the evidence points away from that right now. The little bit of evidence we have, which isn't enough, but because if you had a Dyson swarm around that star, you would at least had an active Dyson swarm. You would expect to see what they call an infrared excess, which is you would see waste heat from this thing. It would be generating electricity, but there would be a lot of heat. You can't. Ultimately, the energy has to go somewhere, and it ultimately goes to where it's not free energy and you lose it. So that what happened was that they looked in infrared at several bands and they didn't see any definitive evidence that there was an infrared excess. And in fact, a lot of evidence there wasn't. And that leads us away from the notion that it's some kind of active Dyson Swarm. It could be a derelict one, but then Brad Schaefer came in with this monkey wrench saying, look, it looks like the star has been dimming for the last century. And we're still trying to figure out if that's right or not. And not everybody believes him. So now, if you're that guy on the History Channel, you just say, aliens! But thank you, James. That reminded me of that. But we really don't know. Tabby Star is certainly anomalous. Nobody has a model yet that they've really done the math that shows what it could be. So,
and our observations are set at such an infancy that we're seeing things for the first time that are probably exceedingly common out there in the great vastness, but we're glomming onto it. Of course, we're seeing it for the first time and we're assigning things to it. I mean, the universe is extraordinary. And so when we find these things that we've never seen before, then wow, this big interest in it. But, they might be a dime a dozen. We don't know yet.
Well, we do know that in the Kepler field, that this is unique, but that's all we know. So it's a small sample, well, not a small sample, but a modest sample of stars. We haven't seen this.
But the point is well taken that we're still in the earliest period of radio astronomy, which is a science only goes back to about the 1950s. So we're seeing a lot of things new for the first time that if we had been doing radio astronomy for hundreds of years, like we've been doing visual astronomy, the longer you're at something, the more you know about it, and you're less surprised.
I think most astronomers will tell you that it's rare that they get a lot of money to do anything, and usually the money gets channeled into specific things like the Hubble Space Telescope or the James Webb Space Telescope that can only observe a very tiny portion of the sky at any one time, and while those telescopes are fantastic, you don't, the amount of money put into radio astronomy has been pitiful by comparison to what the kind of astronomy that produces pretty pictures.
But what's really cool about that, though, is that there's this huge cadre of amateur astronomers that I think are making great contributions to our knowledge right now. And, they're doing that on their own time after their 9 to 5 and they settle in for a beer and hit the skies, with their astronomy telescopes. I think that's been very helpful.
Oh, yeah. Well, the Association for Amateur Variable Star Observers,
they're finding a lot of things.
They are extremely good astronomers. None of them get paid for it, or very few of them do, but probably none. Many of them have a lot of training and know what they're doing, and have a lot of experience. And there's also the Occultation Timing Association, which times stars as asteroids and planets pass in front of them. These folks are very good at what they do. Yeah. And then on top of that, you have the citizen science people like the Planet Hunters, which really found Tabby Star.
Yeah.
To be, they were the ones who pointed it out, said this one is weird, and brought it to Boyajian and et cetera's attention. Hey, why don't we do something about this? And that's now the whole Tabby Star thing. We're going to cover again in the future very soon, both here and on the WOW signal. And I'll have more announcements to make about that, hopefully in the very near future. We have been talking about this for about an hour and 20 minutes, so I think we're time to wrap it up. So what I'm going to do is go around, and I'm also going to ask each of my panelists for a recommendation. Now, the recommendation does not have to be related to anything having to do with radio astronomy. It can be anything you like. I know mine has nothing to do with it. It can be anything from a website to a movie to a song, you name it, whatever, just go for it, whatever you like. So let me see. Do we have? Okay, we have Adam back. Let's start with Adam. Your final thoughts and a recommendation.
First off, I'd like to recommend a project called Einstein at Home, which is a data crunching citizen science project. You don't actually have to do anything yourself. You just hook your PC up to some software called Boink, B-O-I-N-C, Boink. You can Google that. You'll find a project called Einstein at Home that looks for pulsars in our own galaxy. We talked a little bit about pulsars earlier. Help find pulsars, particularly ones towards the center of our galaxy that seem to be absent for some strange reason. My thoughts on fast radio bursts are that we just happen to be at a point in time where we don't know exactly what they are, we don't know exactly where they are, but we will find out. I'm sure of it. It's just a matter of time. They're building a big radio telescope in China. They're building another one in Canada. We've got the square kilometre array in South Africa to come. And the future of radio astronomy is pretty bright. So I would expect this mystery to be solved within a decade. I'll leave it at that.
All right. So we not only have a recognition, we have a prediction from Adam that solved within a decade.
Yeah.
Okay. James, are you there? I'm not sure what happened to James. Okay. Well, Marsha, let's go to you.
Oh, yeah, I definitely can recommend the movie Ex Machina. I just recently got around to watching that, and it has to do with artificial intelligence and the fact that applying the Turing test for artificial intelligence turned out to be exceedingly woefully inadequate, in that this particular strain of AI was far beyond what anybody could imagine that it could become. And I found it in the area of transhumanism and artificial intelligence. It was a movie that really adds a lot of value to that subject, Ex Machina.
Yeah, and I've seen that too, and I think at the end I'm wondering there's got to be a sequel there.
That's what I was thinking too. I hope so.
She's out in the, she's out in the wild, and nobody knows that she's a robot. Yeah, so.
Well, she isn't, as far as she's concerned.
Yeah. Well, I don't want to give away too many spoilers, but yeah, definitely go see that. Or you can bring it up on what. Well, we watched Netflix. It on the Apple TV. There's lots of ways.
Yeah.
James, you're back. James, final thoughts and a recommendation. I can't hear James. James, are you there? Okay, let's go to Nick.
I would like to reiterate what Adam said, that the future of radio astronomy is very bright. Paul, you were saying earlier that it gets very little money. I hope it gets more money in the future. And I think that once we get a sensitive radio astronomy telescope on the dark side of the moon, which is shaded from the electromagnetic radiation.
Far side, please. Thank you very much.
Excuse me. The far side of the moon.
You're not Pink Floyd after all.
I am looking forward to some really incredibly interesting anomalies that are likely to be discovered, and which will be the spur to the advance of scientific knowledge. And so I think that radio astronomy has a very bright future indeed. And I hope we have a lot more mysteries. I hope we have a lot more puzzles and mysteries that we can work our way through and put the pieces together and get a better picture of our universe by and by.
You trying to get a mainstream media job by saying mystery a lot?
For my recommendation, I would like to recommend a tweet. There are people out there who do what's called Twitter fiction. That means they write a story within 140 characters. And I ran across one last week that I thought was quite funny. James Miller at A Small Fiction wrote, "We scattered our signals across the cosmos searching for life. When the reply came from the stars, it decoded to one word: unsubscribe."
Oh, too cruel. Okay. James, are you back with us yet?
I think so.
Okay, yeah. I hear you.
Okay.
Go ahead.
Yeah, I was going to say my recommendation is, as you know, I've got a small child. He's just starting to get into a lot of different topics, and I found a podcast called Brains On. And I thought it was zombies at first, but it's actually a multi-topic science podcast geared towards younger children. And it's a lot of fun, and my 6-year-old doesn't understand all the topics, but he grasps enough of it. You know, they use the language in a manner of speaking that he can get the ideas pretty well.
Okay, well, way to go, Colin. And you've got an even younger one that's not quite ready for that, but
no, but he's gabbling up a storm.
Okay, great to hear that. Okay, my final thoughts are that I kind of echo the other folks. I think that FRBs are hopefully a stimulus to get a bit more money and attention on radio astronomy. We only have a few really great radio observatories worldwide. Although the Square Kilometer Array, which is an international project largely driven from Europe, should be coming online the next few years and will be a big advance in sensitivity. And we are also looking at, there's a kind of an exploratory project to look at expanding the Very Large Array, which, as you know, is in New Mexico, to the next generation, which would also be comparable to the Square Kilometer Array in sensitivity, maybe a little bit beyond that. So I hope that the FRBs help to spur the funding for that, which is something that those folks are going to have to fight for tooth and nail if they want to build the next generation VLA. As far as getting one on the far side of the moon, I'm all for it. I just don't know if I'll see that in my lifetime because of the expense, but I would hope so. My recommendation has nothing to do with FRBs. It's that I know of anyway. It's The Hollow Crown, a series of films of 4 historical Shakespeare plays: King Henry King Henry IV, Part 1, King Henry IV, Part 2, King Henry V, and Richard II. The direction is really, really good in these plays. They do a lot with a reasonably small budget. The battle scenes aren't bad, considering that they didn't have that many stunt players to work with. And they have intelligent cuts, and one of the best Falstaffs I've seen in Simon Russell Beale. So by all means, check out The Hollow Crown. And you should probably have, if you're like me and speak colloquial American English all the time, you're probably going to need to have the text with you side by side as you go through it, and probably have to go through it a couple times to get everything. So that's The Hollow Crown, and I'll have a link to that in the show notes. I'll link to everything in the show notes. I would like to mention, before we sign off, that we do plan a Douglas Adams episode in May. I believe May 20th is the date. I'll check that. If you'd like to be on that panel, even if you don't want to be on any other Unseen Podcast panel, email me at unseenpodcast@gmail.com, and we'll consider adding you to the list of people who want to be on that panel. If you want to be on the Unseen Podcast panel in general, send an email to the same address, unseenpodcast@gmail.com, or just come over to Google Plus and join our community. We'd love to have you. The Ideal Panelist is on just a few times a year. You don't have to be on it's not your regular Friday night gig. You can do it just once in a while, like Marsha does. And you can come on and express your opinion, and you can also, it's very important that the panelists come in and help us shape the topic that we're going to be discussing for that particular show. The invitations go out about a month in advance, so you have plenty of time to think about what you want to discuss and help to contribute to that discussion. Now, this is a spin-off of the WOW Signal, and I hope you'll follow the WOW Signal as we go through further in-depth interviews on both this topic and Tabby Star as well. Go to wowsignalpodcast.com. For more information on the Unseen Podcast, go to unseenpodcast.com. There we have a list of all our episodes, and you can download any of the back episodes. This is episode 45, and not enough of you have downloaded our discussion with Bob Novella. That was episode 43. Bob, if you're listening, give us some more promotion so we can use it. The episode 44 is done quite well, by the way. That was our discussion on contact with ET civilizations. So we hope you'll listen next week. We should be back with another episode. We've not settled on the topic for that yet. If you want to weigh in on what the topic will be, you can do that. You can go to our Unseen Listeners subreddit on Reddit, or you can come to our Unseen Podcast Listeners community on Google Plus, or you can join our Unseen Podcast Participants community on Google Plus, or you can just email unseenpodcast@gmail.com. If you want to support this podcast, we will accept your support gladly at patreon.com/unseenpodcast. And thank you for listening. Our music has been by DJ Spooky, and our panelists have been Adam Smith.
Thanks.
And James Garrison, who is inaudible, and Marsha Barnhart.
It was a pleasure, Paul. Thanks for the invite.
And Nick Nielsen.
Thank you for the opportunity.
And thanks, guys. And we'll see you back next week on the Unseen Podcast. Again, unseenpodcast.com. Let us know what you think. Good night.